So every time you run an experiment, you get a slightly different answer. And why is that? Well, there's certainly just basic measurement error due to the precision of your devices. You can also have random uncontrolled factors like vibrations in the room or noise. Who knows? It could be something that you never figure out, but for some reason, you know measurement is exactly the same twice. So if you ran 1,000 or 1,000,000, or let's be real thorough. Let's run 100 million experiments. You could average this random noise out. This error would basically go away. Now, you then come up with an average answer, a mean, that we call mu. And that average represents the average over an infinite number of repetitions. So it's defined, that's what that triple equals represents. It's defined as the average over the whole population of experiments. Now, being that you have limited resources, limited time, limited patience, you're only going to do, let's say, n experiments. And then you'll come up with some average that we'll call x bar. So that's just defined or equal to the sum over each measurement, xi, divided by n. That's how we calculate the average. So xi is just the ith measurement. So this is the population mean, and this is your sample mean. And they're not going to be equal. In general, now, hopefully mu is going to be pretty close to x bar. Hopefully your sample's nice representative. But we'd like to know how far. We'd like to be able to establish some confidence around x bar, some interval, and say, okay, we estimated the mean to be x bar, and we think that the true mean is within so far from x bar. So how do we do this? Well, first of all, we need to have some measure of dispersion. We need to have a way of measuring how scattered our measurements are. So really an assessment of how repeatable your experiment is. So the way to measure dispersion is with the standard deviation. And for a finite number of points, we use an expression for this sample standard deviation that looks like this. This is often important for quality assurance. If you're making some widget that's got to be, let's say, so big, you just can't have too much variation in that size, right? It won't work in the machine you're putting it into. So this would be a quantity that you can calculate on your batches of widgets to make sure that they're all pretty much within spec. Now let me explain this. So we're summing up the difference between each point and the mean. Well, if you sum that up, you get 0. What we're summing up is the square of that. You see the square? And that's important. It also means, it It doesn't matter whether you're above or below the mean, just how far. And then we divide by n minus 1. Why n minus 1? Well, it has to do with the fact that the sample standard deviation tends to be biased. But the simple, cheeky answer is if it matters whether this is n minus 1 or n, then your n is too small. Your sample's too small. All right, so how can we interpret the standard deviation? So let's say you've got your sample mean here, and I'm going to plot on this x-axis. This is just the number line. This is values of x. And over here is the probability of you actually observing this measurement. Probability peaks here at the mean, and it drops off in a bell curve for many distributions, many actual experiments. This is what you observe. High probability of getting values near the mean, low probabilities of getting values far away from the mean. So S helps us measure how wide this distribution is. If you go two standard deviations in either direction, you will include 95% of the data. So 95% of the area under this curve, 95% of the possibilities. So one thing we can do is we can say, all right, this sample mean plus or minus 2s includes 95% of the data. That's not ultimately our goal here, though. Remember, our goal is to estimate the population mean. The true mean, if you took an infinite number of measurements. So what we just had there with the standard deviation is an estimate of dispersion of a single point. It says, given any one point, how much is it going to be spread? But what we're looking for is a population mean, an estimate of it. And means are less scattered than individual statistics. And so we use a different measure of dispersion. The dispersion of the mean is S over the square root of n. So that was what we were using before. It's going to be smaller with the square root of n factor. And that's called the standard error. Standard error is then used to bound our population mean. The population mean should be with a 95% confidence interval and that's for 95% confidence with 20 measurements in our data set. So where does this number 2.09 come from? You might be wondering. It seems a little arbitrary. It comes from what's called the student's t-test, something you'll learn about in Prob Stats 273. And as n goes up, this number goes down. If you have an enormous, like thousands of data points, this number drops slightly below 2 to 1.96. But for what we're doing, this is good enough. All right. So to summarize, you're going to go out, you're going to take about 20 measurements, calculate the standard deviation, then divide by the square root of n to get the standard error. And you can use that to bound the true mean of your population of data. Now, a few points to remember. If you find that this confidence interval is unacceptably wide, you can increase n. Increasing n slightly reduces this number. You have to look up the student's t-test to learn more about that. Brings down the standard error due to that square root of n. You can bring down the variance also by changing the physics of your experiment. Start paying attention to some of those random, uncontrolled answers. Spend more money on precision in your devices. One thing this doesn't apply to, though, is deterministic errors. Deterministic errors are things that create biases, things that can be corrected for. I'll give you an example. If you're trying to measure engine's efficiency, friction almost guaranteed to always reduce the efficiency. It's not randomly increasing it or decreasing it. If you're trying to measure a person's weight, sure, you might repeat the weight measurement many times, but the effect of my clothing is always going to bias that weight measurement too high. And so that kind of error, you subtract a couple of pounds for the weight of my clothing. And that kind of small correction, by the way, is well worth doing, even if you don't know the weight of my clothing very precisely. The other thing is... Oh, there is no other thing. Let's quit there. Thank you.